Okay, so today I will discuss a very important theorem in mathematical analysis. It is also a very important theorem used in applied maths also. So this theorem is known as the Stone Weierstrass Theorem. I will make two videos to illustrate this theorem properly. In the first video, or that is in this video, I will discuss the development of the background to understand the proof of this theorem, and in the second video I will discuss the proof of this theorem and some of its corollaries. So let us begin our first video. So this is the table of content. First of all, I will discuss about a little history and some genesis about this theorem, the development of this theorem, and then I will discuss about some settings that are required to know the proof of this theorem, to understand the proof of this theorem. And there is a lemma, and then the main theorem and corollaries and some applications. So when we see the genesis and its history, we can see that this is a very important theorem and it is a general theorem. Stone Weierstrass theorem is the generalization of classical Weierstrass theorem. Weierstrass in 1895, he showed that the polynomials over the closed interval 0 to 1 are dense over the set of continuous functions over this compact or closed interval 0 to 1. It means what? Dense means take any continuous function f. Suppose f is any continuous function and its domain is closed interval 0 to 1, and you have any epsilon greater than 0, then the set of polynomials is dense in this space. It means for this epsilon greater than 0, you will find a polynomial p such that the norm of f minus p is less than epsilon. It means p is in the epsilon neighborhood of f. So this is the classical Weierstrass theorem that was given by Weierstrass, a famous late 90th century mathematician. But after one decade, or after nearly half century, not one decade, after nearly half century, in 1948, another mathematician come, Stone. Actually, he was preparing a lecture note on the Weierstrass theorem, on this Weierstrass theorem, and then he realized that this theorem can be generalized. In the classical Weierstrass theorem, Weierstrass consider closed interval 0 to 1, and then Stone realized that we can generalize this closed interval 0 to 1 by compact space in topological, in Hausdorff topological space more specifically. So actually we can take ck means space of continuous functions over over compact space k. So we can take ck in place of c01, where k is compact set, and we are looking on a subset of continuous functions in place of polynomials over k, which is unital subalgebra of ck. What is unital subalgebra? We will see it later. So in classical Weierstrass theorem, Weierstrass showed that you pick any element from C01, it means you pick any continuous function from the closed interval 0, 1 and any epsilon greater than 0, you will find a polynomial. in that epsilon neighborhood. It means the polynomials are also continuous functions. So set of polynomials is a subset of say, C01. So set of polynomials is dense. A subset of C01 is dense in C01. And then Stone realized that we can generalize this subset of polynomials, and we can first he generalized C01 to Ck, then he generalized this polynomial set by a unital subalgebra of Ck. What is unital subalgebra of Ck? I will discuss it later. So space of polynomials 01 is a particular unital subalgebra. When Ck, we take the particular case of Ck as C01, then we take the particular case of unital subalgebra as polynomials, set of polynomials of a 0 to 1. Then this classical Weierstrass theorem become the particular case of the Stone Weierstrass theorem. So this is very beautiful theorem. So by proving this Stone Weierstrass theorem, actually we are proving classical Weierstrass theorem in a different and very beautiful and very general setting way. So now we'll see some required mathematical tools or the settings which are required to know before proving the Stone Weierstrass theorem. So once you go through these mathematical settings, first thing is metric spaces. So most of us already know what is metric space from our undergraduate courses. So metric space is just a pair xd where x is a set and d is a function from x cross x2 are satisfying some properties that are non-negativity, identity, symmetry, and triangle inequality. And the other setting is normed vector spaces. Most of us also know about this from undergraduate course, I think. Normed vector space is nothing but a special kind of vector space along with a norm. If V is a vector space and we have a norm is a function from V to F cross V to R. So it has some properties that norm of x is greater than equal to 0 and norm of x is 0 if and only if x equal to 0, and norm of alpha x is equal to modulus of alpha times norm of x, and norm of x plus y is less than equal to norm x plus norm y. This is known as the triangle inequality. So another setting is topology. Topology is a new concept, comes almost in postgraduate courses. Topology is also nothing, it's also simple thing. Uh, you take a set X, and topology is collection of specific collection of subsets of X. It is denoted by tau. You can see tau, and it is such that it has three properties. The first property is the empty set, and set X itself will be a member of tau. And the second property is the arbitrary union of the elements of T should belongs to not T, tau should belongs to tau. And a finite intersection of the elements of tau should also belongs to tau. Then we can say that tau is a topology on the space X. Now we need a special kind of topological space. So it is topology. When we take X and tau together, then it is called a topological space. So we need a special kind of topological space here that is called the Hausdorff topological space. It is a special kind of topological space. X star is called Hausdorff if for any two distinct points x, y in X there exist disjoint open sets u, v in tau such that x is in u and y is in v. Elements of topology is called open sets. In higher mathematical area, in pure mathematical area, or in higher mathematical area, when we talk about the abstract structures, topology, then the elements of topology itself is called an open set. So Hausdorff topology is what? Hausdorff topological space is a special kind of topological space. First of all, it is a set along with a topology, and it has a property that whenever you took two different points from that space, you can have two different elements of the topology, that is two disjoint open sets, such that one open set contain one element, another open set contain another element. It means what? It means that in Hausdorff topological space, we can separate two distinct points by the help of open sets, and that's it. And now we need some properties of continuous function, characterization of continuous function. A function from one topological space X to another topological space Y, when we call a function to be a continuous function. So these 2 points, here 1 and 2 points, are equivalent to each other. F is continuous means if you have a sequence xn converging to x in the domain, then the sequence in range f of xn should also converge to f of x. Then we say that f is continuous. Then whenever f is continuous, then in the second point, you take any open set in Y, its preimage f inverse of u will also be open in X. So these are the characterization of continuous function. Now, characterization of compactness is also needed when we say a set is compact. If X is a metric space and A is a subset of X, then following are equivalent. We say A is sequentially compact. Sequentially compact means every sequence in A has a convergent subsequence having limit in A itself. When A is sequentially compact, then second point also valid, that A is complete and totally bounded. Complete means every Cauchy sequence converges within A itself, and totally boundedness means for every epsilon greater than 0, there is this finite cover, finite points x1, x2, xn in X such that A is covered by the epsilon neighborhood of these xi's. Okay, so how we prove this? The Bolzano-Weierstrass approach to prove the uh, convergent subsequence is that in first of all in finite dimensional space, what he had done, he take a set of sequence and then he divide it in two parts. We can divide two parts in finite dimensional cases only. In Rn, we can divide it. So he divided two parts of the sequence points. Since sequential points have infinite points, so at least one of the two parts will contain infinitely many points. So the part of infinite points, we again divide that part into two parts. And again, at least one of them will contain infinitely many points. And then we do this process so on and take points, 1 points from each parts having infinite points, then it forms a sequence which is convergent subsequence of the given sequence. But when we are talking about in general setting, when we are not in the finite dimensional case, we do not know about the dimension at all. We are in topological spaces where we have only the open sets. Then this idea is generalized. Then we take finite number of balls which has the infinite points. So at least one of them will contain infinite points because we cover by finite number of balls and there are infinite points. So one of them should contain infinite points, otherwise it will not cover. And we take the ball such that we can make radius as small as we desire. So we can take very small radii balls and cover the whole set by many but finitely. And at least one of these balls will contain infinitely many points. And again we do the same process with that open balls. We cover that open balls with finitely many open balls with small radius but finitely many, and again one of them will contain infinitely many points, and we do this process continuously, and we take points from all those infinite points containing open balls, and then in this way we can take a convergent subsequence. So this is the Boltzmann-Weierstrass approach to construct a convergent subsequence from given sequence in sequentially compact space, I think. And the third point says that every open cover of A has a finite subcover. It means if you have an open cover UIs of A, means A is a subset of union of UIs, then you can cover A by finitely many, taking finitely many of UIs. That's it. So these are the characterization of compactness. It means any one of these, if a set, you have a set or you have a space A, we satisfy any one of these conditions, then it is compact set. And now the second thing is algebra, and we had talked about the unital subalgebra. To understand the unital subalgebra, we need to understand what is algebra itself. So this algebra is not the algebra of the major theory. It is an algebra in another sense. In Banach space, we talk about this algebra in Banach space in functional analysis. So algebra is a special kind of vector space over field of real numbers or field of complex numbers. So A is algebra over R or C. It is a vector space equipped with a bilinear multiplication across A goes to A. It means what? It is nothing but if you know about the vector space. So in vector space, what we know that we have two kinds of operation. One is vector addition and another is scalar multiplication. So in with respect to vector addition, the vector space is an abelian group, we know this. But we do not have the multiplication uh, operation of the elements of vector space. We have the scalar multiplication. It means we can multiply the elements of field with the elements of vector space. We do not have any operation so that we can multiply an element of vector space with another element of vector space itself. But if we have this kind of operation, this kind of bilinear multiplicative operation also, then the vector space is an algebra, is said to be an algebra over R or C. Now we are talking about the Banach algebra. Banach algebra is, as a term suggests, it is an algebra and it is a special kind of Banach space. Banach space is nothing but a normed linear space, a normed vector space which is complete. If a normed vector space is complete, then it is called the Banach space. And a Banach space which is also algebra and having properties that norm of x into y is less than equal to norm x into norm y for all x, y in A, and it is complete with respect to this norm, that is called the Banach algebra. A Banach algebra is called unital if it contains an identity element E. E's identity means E into x equal x into E equal to x for all x belongs to A. And what is unital subalgebra? So we know about what is algebra, what is Banach algebra, and when we call a Banach algebra to be a unital Banach algebra, if it has identity, then it is unital Banach algebra. Now, what is unital subalgebra? As the name suggests, it should be unital, it should have identity. It subalgebra means it should be an algebra, it should be a subset of an algebra and itself an algebra. So it will be unital subalgebra. So if A be a unital Banach algebra with identity E, and a subalgebra B subset of A called a unital subalgebra if B is itself a vector space of A and x into y is in B for all x, y in B, and E is an element of B itself. So now we have done all those mathematical settings and equipments which are required to understand the proofs of Stone Weierstrass theorem. Now I will discuss a very important lemma. We will use this lemma for proving the Stone Weierstrass theorem. This lemma says that if A is a subset of Ck, Ck means space of continuous function over compact set K, and B be a closed unital subalgebra, then the first point says if f is an element of A which is greater than equal to 0, means f is positive, it is pointwise positive, means if you take any point of K, take x is a point of K, then if you take value of f at that point x, then f of x will be greater than equal to 0. So if you take any positive function from A, then its square root will also be in A. And the second claim is that if f is in A, then its modulus value will also be in A. And the third point is that if f and g is an element of A, it will implies that minimum and the maximum of f and g will also be an element of A. Again, minimum and maximum are the pointwise properties. Means first of all we take a point from K, then we take the value of fx and gx, and then we take the minimum value of fx and gx, and that is the minimum fg at point x. So we'll do this all operations over whole compact space K, then we find the minimum fg as a function in A and maximum fg as a function in A. So we'll prove this lemma. So first of all, we see that mod of f, we can write mod of f as the square root of f square. Square root means f square to the power 1 by 2, and 2 get cancelled and we will left off out of the mod f. The second point, minimum of fg. So there is an identity of finding the minimum of function f and g at a specific point. That is equal to 1 by 2 times f plus g minus mod of f minus g. How it is true? Let us suppose at least one of them should be minimum. Suppose f is minimum among f and g. Now if f is minimum, so f minus g will be negative. So mod of f minus g will be negative of f minus g, means g minus f. So when we subtract g minus f from f minus g, then we get 2f, and we divide by 2, then we get f. That is the minimum of fg. And same when g is minimum, then f minus g is positive, then f plus g minus f plus g will be 2g, and divided by 2 will be g. So minimum of fg is equal to 1 by 2 times f plus g minus mod of f minus g. Similarly, we can derive that maximum of the two function fg is equal to half of f plus g plus mod of f minus g. So if in this lemma, if we prove the first one, so if mod f will be in a, then we can say that this minimum of fg, that is nothing but addition and subtraction of the elements of a itself, and multiplication by an element, scalar element. Since a is unital subalgebra, so all of these elements will be element of a if we show that this mod value will be an element of a. Similarly, maximum will also be there. So we need to prove only the first part, that if f is a positive function in a, then its square root is also in a. If you show this, then all the three points will already shown, already proved. So for showing one, we rescale. Suppose f is a positive function, it is given. After rescaling, consider without restriction that f falls within the interval 0 and 1. So if f is greater than 1, I can multiply f by some constant k, so that value of f will decrease and it will fall under the interval 0 to 1. Okay, we do this, and then we define another function g as 1 minus f. Since f is in between 0 and 1, then 1 minus f, that is g, will also be in between 0 and 1. And now we take the square root of f. Since g is 1 minus f, then f will 1 minus g. So ft will be 1 minus gt. Okay. Now, so this will become the form in the form 1 minus x to the power half. In the Taylor series expansion of the 1 minus x to the power half, where modulus of x is less than equal to 1, we see that it is of the form 1 minus summation en x to the power n, where en take the values 1 by 2n minus 1 into 2 to the power minus 2n plus 1 into c2n minus 1 cn. Binary, this is a binomial coefficient of 2n minus 1 n, and it is equal to 2n minus 1 cn, that is 2n minus 1 factorial by n factorial times 2n minus 1 minus n factorial. So we expand this 1 minus g to the power half by Taylor's expansion, and we got that it is equal to 1 minus summation of an gn to the power n, and varies from 1 to infinity. And by Stirling formula, we know that the value of an is given by 1 by 2n minus 1 to rise to the power minus 2n plus 1 times the binomial coefficient 2n minus 1 n. And by Stirling formula, it is strictly less than c times n to the power minus 3 by 2. So Now we calculate this value. Mod square root of f minus 1 minus summation of k varies from 1 to n. Now we do not go to infinity directly. We go finitely. We take values from 1 to n. And we subtract this quantity from square root of f. And now we find that square root of f has value this 1 minus summation n g n to the power gt to the power n is equal to 1 to infinity. Put this value. So square root of f is 1 minus summation n g to the power n and minus this quantity 1 and minus minus plus a k g to the power k. So here g to the power k will be there. So now 1 will get cancelled out, and when we subtract this quantity from this quantity, we will get uh, it is equal to summation of k is equal to n plus 1 to infinity ak g to the power k. So now when we take this norm inside the summation, then this equality becomes inequality. It will be less than equal to summation of ak norm of g raised to the power k, and this ak will go outside this norm because ak is already positive, and again norm of g to the power k is less than equal to norm of g raised to the power k, since norm of f into g is less than equal to norm f into norm g. And again, as we saw that g is in between 0 and 1, we after rescaling find that f is greater than equal to 0 and less than equal to 1, and g is 1 minus f. So g is also in the range of 0 to 1, so norm of g will be less than equal to 1. We put that value here, then we find that this whole quantity is less than equal to summation of ak. K varies from n plus 1 to infinity, and it is strictly less than c times summation k raised to the power minus 3 by 2. Why? Because here we saw that ak, this an is strictly less than c times n to the power minus 3 by 2. So here we put that value. In place of ak, we can take its larger value c times k raised to the power minus 3 by 2. So this inequality becomes strictly less than inequality here. And now this summation k to the power minus 3 by 2, that is summation 1 by k to the power minus 3 1 by k to the power 3 by 2, and by gp series test we can say that summation of 1 by k to the power 3 by 2 is a convergent series by p series test, because 3 by 2 is greater than 1, so the remainder term will go to 0. This is nothing but remainder term. K varies from n plus 1 to infinity. So this is remainder term of that P series. So it will goes to 0 as n tending to infinity. That's the crux. Why it is a crux? See here. We evaluate the value of this. We estimate the value of this norm. Norm, when we subtract this quantity 1 minus summation of akg to the power k, which, where k varies from 1 to n, from square root of f, then the whole norm goes to 0 as n tending to infinity. It means this quantity 1 minus summation akgk, k is equal to 1 to n, tends to square root of f as n tending to infinity in ck, space of continuous function over the compact interval k with respect to sup norm. This norm is the sup norm. It means what? under root f is a limit of this sequence, and the whole sequence 1 minus summation of a k g to g raised to the power k, where k is equal to 1 to n, is an element of A. Why? Because 1 is an element of A, g is an element of A, and this is nothing but summation and multiplication and addition of the element of A itself and a scalar. So it will be an element of A since A is an unital subalgebra. So whenever we multiply two elements of A and when we add, they will fall under A itself. So this whole sequence of elements of A has square root of f as its limit. So square root of f is limit of this sequence, and we consider A, already A is given to be closed. Say it means this square root of f is an element of A. Since we know that if any set is closed, it means it contains all its limit point, and square root of f is a limit point of A. It means square root of f is an element of A, and that's all. We need to prove this for the proving this lemma. So this lemma is proved. So now we will continue our discussion in the next video, lecture video, where we will discuss about the proof of this theorem, Stone Weierstrass theorem, and we will use this lemma for proving that theorem. So okay, thank you, and meet in the next. Hope we will meet in our next video. Thanks.